So this video is a tale of two sulfites. So I'll repeat this later because I had started to record the Moco, the making Moco video. And so this is a little snippet of that video, but I wanted to bring it out and kind of separate it and say, look, there's a tale of two sulfites going on. So if you haven't joined the Moco Steel Recovering from Sulfite Toxicity group on Facebook, you should. Because within that group, as people have shared their stories, we're realizing that there might be a tale of two sulfites. And what I'm going to explain to you in a bit is that your sulfite toxicity could be related to molybdenum cofactor or the sulfite oxidase enzyme, or it could be related to your immune function. And so it's pretty easy to determine who is who based on one particular test for S-sulfocysteine. So, yeah, I'm going to explain a little bit about making Moco again in this first part of this video, and then the rest of the troubleshooting of making Moco will be in a separate video. So moving on. Oh, before I go on, I'm a dietitian, but I'm probably not your dietitian. So talk with your own healthcare provider before you make any changes to your diet, your supplements, your medications, or your lifestyle. This isn't medical advice. This is just me exploring a topic, showing all the problems that could go wrong, and then potential solutions, because no one wants to know just what's going wrong. We want to know how to fix it. And then your job is to take this to your own provider and discuss it, because I don't know your health history. I don't know the medications that you take. So please be safe with this information. All right, now let's get started. So if you don't know about molybdenum cofactor, you're probably like, I've not heard of this. So molybdenum cofactor is shown up here, and it contains molybdenum. You don't just use molybdenum by itself in the human body. It's incorporated into Moco, or molybdenum cofactor. And it's used for 5 enzymes in the human body: xanthine oxidase, xanthine dehydrogenase, aldehyde oxidase, sulfite oxidase, and MARC. It is not used for FAD synthase. So that's something that's been a whisper down the lane situation. I do think that you see resolutions in things that would look like that you have an FAD deficiency whenever you restore your molybdenum cofactor, because it helps to metabolize sulfite, and sulfite is an inhibitor of succinate dehydrogenase, which makes you look like you have an FAD deficiency on an organic acid test. So the enzyme sulfite oxidase is made out of amino acids. So you can see here, this is a picture of a cell. And whenever we make an enzyme or any other protein that's needed in our body, it's made of tiny amino acids that are linked together. And the ribosome is this machinery that does this action, okay? So the sulfite oxidase enzyme is put together with amino acids here by the ribosome, but the instructions that's represented by this green ribbon, those instructions come from your nucleus as messenger RNA, and then that messenger RNA is coming from a blueprint in our body called DNA that's in every cell of the human body. So how it goes in succession is your body will transcribe the DNA for the enzyme sulfite oxidase, and then it leaves, the mRNA leaves the nucleus, and it goes to the ribosome, and these amino acids are assembled into the sulfite oxidase enzyme. But the enzyme is not ready to do its work after it's removed from the ribosome. So once you've made your pre-sulfite oxidase enzyme, that's what we're going to call it. Once you've made that, and it's represented by this green and orange squiggly line attached to this blue and black stick. The blue and black stick is called the leader peptide. So it's leading the pre-sulfite oxidase enzyme towards where it actually is in the cell. Where it is in the cell is inside of the IMS, which is the inner membrane space. And that's where sulfite oxidase does its job. My friend Sergey from Sergey Does Science pointed this out to me, and I was like, wow, that's really cool. I don't think we've thought about that. He's really good about thinking where things are happening in the cell. And we have to think about that from a sulfite toxicity standpoint. What is sulfite oxidase enzyme doing? Well, one, it makes sulfate, so that's super important for our cellular health. But also, it's protecting the mitochondria because sulfite is toxic to the mitochondria. Whenever your sulfite oxidase enzyme is not working, then cytochrome C oxidase can partly remove the sulfite, but what it does is it makes sulfite radicals, and those cause oxidative stress, and that will shut down a mitochondria. And so sulfite oxidase is a protective enzyme for the mitochondria. And that brings into question, what are we doing with sulfite that's outside of the mitochondria? That can happen. The sulfite outside of the mitochondria could be coming from the activity of CDO, cysteine dioxygenase, that's increased whenever the hypoxia-inducible factor 1 alpha pathway is increased, because that enzyme exists outside of the mitochondria and it can lead to more sulfite production. So not everyone is going to be having upregulation of their hypoxia pathway, but some people will be. There's lots of factors that can go into that, and I actually have an entire diagram about that. So these are the modern day lions, all of these over here, that induce the hypoxia pathway, and that can increase CDO expression and activity, and that can lead to more sulfite, specifically in the cytosol. And then that could put a burden on glutathione, but also that sulfite can move to the mitochondria and it can be made into sulfate via sulfite oxidase enzyme. So the classic way to tell if you have a problem with molybdenum cofactor production is to get an OMX test to see if your S-sulfocysteine levels are high, because that is a huge indicator that this enzyme has stopped working. It does not mean, though, that you don't have a sulfite problem, because your sulfite could be outside of your cells altogether. Your reactions to things that also cause problems for people who have sulfite oxidase or molybdenum cofactor deficiency, those reactions could be because your neutrophils are producing more sulfite. So this is a diagram that I made to try to explain why neutrophils would be producing more sulfite. So if you look along here, there's all these receptors along the neutrophil. We have a lot of neutrophils in our portal blood, like along the gut-associated lymphoid tissue, and the goal of that would to be engulfing the bacteria. There's also macrophages too, and macrophages are involved in this process of us feeling so unwell, and I'll explain how they interact in a few minutes. But whenever we have gut dysbiosis, then certain things can activate these neutrophils. And I think that there's a problem going on here where we're losing our adaptive immune system. And many of the people that come to the Moco Steel Recovering from Sulfite Toxicity group have actually come from the low vitamin A diet, because their serum vitamin A was elevated, which has previously thought to be vitamin A toxicity. And it's possible that having high serum vitamin A could be a marker for having a full liver of vitamin A, but really you would want to get a specific test called retinal esters to figure out if your vitamin A is at max capacity in your liver. So it's quite possible that you could have very high serum vitamin A levels, and it's a contributor to having overactivated macrophages. I've done a video on that in the past about nitric oxide and how it's a Goldilocks gasotransmitter. And you can watch that video. I need to go back and watch it and see if I have new information to add to it. But there is, it's definitely not good to have high serum vitamin A levels because it can aggravate macrophages, and then that can make them increase iNOS levels. And then iNOS itself is not necessarily, I mean, technically it's a bad thing, but having nitric oxide is not a bad thing. It's when nitric oxide becomes peroxynitrate, and that can lead to additional kind of crappy versions of radicals that damage the body. And you'll see that in a moment. I kind of sidetracked. But back to this slide. Okay, so let's say we have gut dysbiosis. There are all these bacteria produce this particular compound. I have to say this right. It's a hard word to say. So it's N-formyl methionoleucyl phenylalanine, or FMLP. And so that's one of the activators of NADPH oxidase, or NOX2, that's on neutrophils. LPS can activate via the toll-like receptor 4. TNF-alpha can activate via its receptor. And then this one, that's GM-CSF, it actually stands for granulocyte macrophage colony stimulating factor. Granulocyte macrophage colony stimulating factor. Just repeating it because, yeah, it's a long word, but it's abbreviated GM-CSF, and it helps to stimulate the proliferation, differentiation, and activation of neutrophils, eosinophils, stuff like that. So it helps to help them grow, but at the same time, it increases NOX2. And so what NOX2 does is it produces superoxide. And then the superoxide can be metabolized to hydrogen peroxide in the presence of superoxide dismutase in the blood. And this was specifically copper dependent. Okay, so this one is a copper dependent enzyme. And also, superoxide can spontaneously become hydrogen peroxide as well. And so we have all these increased oxidative stress markers. The hydrogen peroxide then can come over here and interacts with something that's released from neutrophils. It's called MPO myeloperoxidase. And it uses the hydrogen peroxide and various substrates to make oxidants that can kill bacteria. So some of these are this hypothiocyanous acid, and that uses thiocyanate. And cyanide is something that can block the uptake of iodine into the thyroid gland, and it's produced with this other thing that we make when we have excess sulfite. It's called thiosulfate. So if you have thiosulfate plus cyanide, then you actually will produce thiocyanate. And so many of us struggle with our thyroid metabolism when we're struggling with sulfite metabolism in general, because if you don't have sulfite oxidase, then your backup is going to be making more thiosulfate. And this happens in sulfite oxidase deficiency. Thiosulfate levels will go up. So that's pretty interesting connection. And then also you're going to use the hydrogen peroxide and chloride anions in the blood, and that will produce hypochlorous acid. And we have to use glutathione to be able to detoxify hypochlorous acid. And then MPO can also take sulfite that's produced by the neutrophil, which I'll talk about how that happens in just a minute. But that sulfite can be converted into sulfate and sulfite radicals, and those make irreversible glutathione adducts. So they deplete glutathione. And you need to know that this depletion is happening in your plasma outside of the red blood cell. So something that I recently saw with someone who reached out to me who's struggling is that they did a test through HDRI where they had their glutathione levels checked, and overall the glutathione levels were very low. And then the oxidized glutathione, which is the one that's used up, was higher, but overall everything was low. But then when they did Nutra-Eval, that showed that they had normal glutathione status in the red blood cell. So I believe what's happening is that outside of the red blood cell, the glutathione is being used up by all of the oxidative stress that's being produced by the immune system, and not just neutrophils. These are the ones that produce sulfite, the only immune cell that produces sulfite, but also like the macrophages and the eosinophils. The other immune cells doing immune reactions are producing additional oxidative stress, and it's depleting the glutathione in the blood. So then my other idea is that what could potentially be happening is that once you have higher levels of nitric oxide, which I'll talk about in a minute, this can contribute to the production of hydroxyl radicals and peroxynitrate, and then those are going to inhibit your ability to use glutathione within the cell. And sulfite itself can also do this. Sulfite can actually, and like that would be if you have intracellular sulfite issues though, but if you have intracellular sulfite issues, sulfite itself can inhibit some of those reactions that use glutathione. So you might overall have a normal glutathione status in your whole red blood cell, but then if you were to check outside of the red blood cell, you would have a decrease in glutathione availability. And then you would also be on your Nutra-Eval, you would have evidence of lipid peroxides. So that would show that obviously something's wrong. You have a lot of glutathione, but you still have lipid peroxides going on. So something's inhibiting your use of the glutathione with inside of cells. And that could be sulfite or peroxynitrate or hydroxyl radicals. So anyway, back to this diagram. So again, the neutrophil is what is producing the sulfite that will become these radicals, and they can damage proteins. So where does that come from? So let's trace back. So right here, the sulfite can be produced during the phase where your neutrophil is going through phagocytosis, and it engulfs this bacteria, and then inside the phagosome, the superoxide will convert hydrogen sulfide into sulfite, and that can come from cysteine metabolism within the neutrophil, or neutrophils are also capable of taking up hydrogen sulfide and producing sulfite from that. And where do they get their hydrogen sulfide from? Well, it comes from the blood. And one thing that individuals with sulfite issues struggle with is typically you have a bad reaction to garlic. Garlic is supposed to help us. It's supposed to inhibit nitric oxide synthase. And so, that would actually not be a bad thing, since we know, and you may not know this, but when you have too much LPS, that can induce inducible nitric oxide synthase. And so an oxidative stress, like those things will increase that. So a lot of times it's like we'll use garlic because garlic will inhibit iNOS. But the problem is that garlic also increases hydrogen sulfide production by red blood cells. Jenny pointed this out to me. It's something that Greg Nye has said, and there's evidence of it. So that could be the reason why you're struggling. When you consume garlic, your red blood cells will make more hydrogen sulfide, and then that hydrogen sulfide can be taken up by neutrophils, and then the neutrophils will make sulfite. And then another possibility is that the hydrogen sulfide is coming from your gut. That's a highly possible thing, right? We've heard about, that you can get too much sulfur metabolizing bacteria in your gut. So let's look at those different ones. Oh, yeah, let's look at that. And then we'll look at one more thing. So there are taurine respiring bacteria. These are bacteria that take taurine, so like taurine supplements. They will consume that, and in a B6 dependent manner, they will produce hydrogen sulfide. And in your blood, hydrogen sulfide can react directly with superoxide and become sulfite. So it doesn't even have to go through these neutrophils. If you have excess superoxide, which would happen if you have specifically a copper deficiency, because the SOD in the blood requires copper. So if you have a copper deficiency, the hydrogen sulfide from your blood can become sulfite. And then this might be the reason why sometimes when people start taking B6, some of the bacteria are going to get some B6. And if you have taurine respiring bacteria, you may have an uptick in symptoms because you're going to produce more hydrogen sulfide, or actually these bacteria will. Another group of bacteria are sulfate reducing bacteria. And these guys are molybdenum dependent. So they can take sulfate and make hydrogen sulfide out of them. The problem with that is that if you have high dose molybdenum supplements, it's possible that these bacteria would use that molybdenum to do their own work. There is an in vitro study showing that if you do high dose sodium molybdate, that particular form of molybdenum will inhibit the ability for these bacteria to convert sulfate to hydrogen sulfide. The benefit of that is that means that you have more sulfate, right? The problem is what is the dose that's needed? It's not like you can take the molybdenum all day. So it is possible to do that. And it might be why some people really do better with sodium molybdate, but very high dose molybdenum is tricky because it has been shown to cause kidney health issues. And I talked about that in a previous video that you can check out on my YouTube channel. And I talk all about molybdenum. So another thing to consider is that the sodium molybdate might inhibit some of the production of hydrogen sulfide from sulfate in your diet, but it's not going to stop the metabolism of taurine or cysteine into hydrogen sulfide. So it doesn't fix all the problems because you still have these cysteine metabolizing bacteria that metabolize cysteine in a B6 dependent manner to hydrogen sulfide. Okay, so that's where all this hydrogen sulfide is coming from. And then one more thing can happen. There could be sulfate from your blood can be taken up by neutrophils, and it's converted first into PAPs. I don't have this on the slide, but it's converted into PAPs, and then PAPs reductase converts it to sulfite, and this is triggered by LPS. So one thing that people struggle with is we're told to do magnesium sulfate baths when we're in a low sulfate state because sulfate is so very, very good for us. And I 100% agree with that. But I found that every single time that I took a magnesium sulfate bath, I had a horrible reaction. And I would wake up with my heart racing and feel horrible. And I think it's because I was providing the sulfate, and I have lovely lots of neutrophils working hard all the time, and they were making sulfite, and it was worsening my symptoms. I even had one client have like an insane histamine reaction and an asthma flare after taking a magnesium sulfate bath. And sulfite is a known trigger for asthma. So again, just caution. I'm not saying don't do it. Just be careful and gentle with your body. Maybe doing a foot bath. Jenny Jones, PhD, recommends foot baths. She highly believes in being gentle, and I think it's a wonderful approach for many of the people out there that are fragile. So before I go on, I want to talk about myeloperoxidase antibodies. So some of us have myeloperoxidase antibodies, and that increases the production of myeloperoxidase. And it would make everything worse, obviously, because you're going to have increased activity of this, and increased activity of MPO is going to cause very high levels of hypothiocyanous acid. And so for these people, it might be helpful to look into things that would inhibit MPO. But just realize that if you inhibit MPO, you definitely are going to have less of these very damaging sulfate radicals, but you're going to have more sulfite. And it's the sulfite that can bind to the specific nutrients in the body that I'm going to talk about. What actually is causing the anti-MPO antibodies? Specific infections can trigger that autoimmune issue. One is staph infections. Another is coccidioides or subacute endocarditis. People who have that from staph or strep will actually be more likely to develop anti-MPO antibodies. If you've had a history of EBV, it might be good to get your anti-MPO antibodies checked. The COVID vaccine is associated with this as well as the hepatitis C, not the vaccine, but the hepatitis C virus can cause anti-MPO antibodies. And then the cytomegalovirus can also do this. So then you need to work with a practitioner on whether or not you want to try to decrease your MPO activity. For example, ginger can do this. Ginger has been shown to decrease MPO activity, but I find that some people react to using that as a supplement because, again, if you decrease MPO, even though it's helpful and it can reduce a lot of the oxidative stress, what you end up having is one, a lot of hydrogen peroxide potentially, and then also a lot of sulfite hanging out. So, one more note on here. If you're not able to read things, these things that activate neutrophils, they're actually increased during COVID. So a lot of people, COVID was their breaking point, right? And so that's when neutrophil levels just like the activity of them just goes sky high. So what I propose is that we don't have just one tail, right? We have multiple things going on. And I wanted to talk to you specifically about the extracellular sulfite and how it can cause B1 deficiency. So once you become B1 deficient, your pyruvate levels will build up, and pyruvate is a signal to the HIF-1alpha pathway to turn on, and that will increase CDO, and that will lead to intracellular sulfite, okay? But what I think could be the triggering factor that brings someone to this high CDO activity and higher intracellular sulfite levels is actually extracellular sulfite. Okay, so there's lots of ways to get a B1 deficiency. It's not just sulfite, so I'm not saying it's only sulfite. Like you can drink 4 cups of coffee a day and induce the B1 deficiency. Or even tea could do that because it's the caffeine, right? Caffeine can deplete your B1. It could be eating a lot of raw sushi. It has like thiamine antagonists in it. Or maybe being on metformin can decrease your B1. If you're interested in more information about what could go wrong with B1, Elliot Overton's a great resource on that, as well as Dr. Chandler Mars. So reach out. You would go to Hormones Matter for Dr. Chandler Mars, and you can read her lovely articles about B1 deficiency. So I propose that during COVID, many of us, because of that uptick in neutrophil activity, develop a B1 deficiency. So because this slide is helpful, it will show you that B1 is the irreversible mopper-upper. So I'm from Texas, and I don't think I have a Texas accent, but then people from not in Texas say I do. So I'm originally a Yankee. I'm from Pennsylvania. But anyway, I like to say mopper-upper because it's kind of like a Texas way of saying it's getting rid of the sulfite. But when B1 is exposed to sulfite, it's destroyed, and it makes a sulfonate and a thiazole. And you don't get the B1 back. It's irreversible. Water forms of B1, water-soluble forms of B1 are the most vulnerable. So the B1 that we get in our diet is in the form of thiamine pyrophosphate. So that one's easily destroyed by sulfite. And if you think about how nutrients are absorbed, your B vitamins are absorbed into your blood and then they enter into the portal vein. Well, that's actually where LPS and all these bacterial compounds are. And so your neutrophils are if you have gut dysbiosis, your neutrophils are going to be producing sulfite. And that's where your B1 is the most vulnerable, is like on the way into the body. So thiamine HCl is also vulnerable, and even thiamine mononitrate. And I really caution people about thiamine mononitrate because I have had people message me to say that they were doing okay until they started that particular supplement. And I think it's because the nitrate, there's actually bacteria in the gut that can convert the nitrate into nitrite, and then you can make nitric oxide. Like spontaneously during acidosis, you can produce nitric oxide. So being in a very high nitric oxide state is not good. It's a Goldilocks gasotransmitter. And you'll see in a minute that too much nitric oxide is a contributing factor to some of to actually producing too much hydroxyl radicals, and that can cause worsening problems related to B6. So back to B1 though for a bit. So TTFD can bypass the sulfite that's being produced in the gut from the neutrophils. But once it gets into cells, it requires glutathione for activation. And so people who have chronic oxidative stress are often in a low glutathione state, and it sometimes can worsen the whole situation. I tried TTFD. I think Elliot Overton is brilliant. I love that he made a very clean supplement because a lot of people are allergic to fillers. And so I have TTFD here at my home, and I even started with a tiny dose. I opened the capsules and I sprinkled a little bit out, but I would get these excruciating like headaches, and it was not because I wasn't getting enough potassium or magnesium. I was monitoring that. I mean, I'm a dietitian, so and also I listened to Elliot's talks. I didn't just blatantly start taking a supplement without even thinking. But I think it was because I overall had a very low glutathione state. Yeah, we learn from our mistakes, right? But I still have it here. I hope to be able to use it someday, but I don't think right now is the right time. So I will keep it. I don't know. I'll have to look at the label to see how long it can last. So anyway, it's not good for someone in a glutathione deficient state. Then benfotiamine can bypass the sulfite problem in the portal vein, but it requires intestinal alkaline phosphatase to be made so that it can be absorbed. And so that can compete with all the B6 in our diet, because all the B6 compounds in our diet contain phosphate, and they have to have the phosphate removed. And even P5P supplements require alkaline phosphatase, because anytime B6 is going to enter a cell, then this over here is B6, P5P, the phosphate group has to be removed. And the majority of the B6 that's in our blood is the P5P form. We definitely can have other forms in our blood, but this one is the major circulating form, and it's bound to albumin typically. And now, when it's bound to albumin, the aldehyde group is protected. Okay, so if we want to be able to absorb our B6, then we need to make sure that we take it away from benfotiamine. And so that's something to consider. Another thing to consider is that benfotiamine, if you have glutamate issues like glutamate dysregulation, benfotiamine, it increases your NMDA receptors in the brain. I actually took this supplement for 3 years, hardcore, despite going downhill, despite taking all the cofactors. And it will increase your NMDA receptors in your brain, but it also can downregulate GLAST, and it can downregulate GLT1, which are glutamate ways you uptake glutamate from the synapse. And I think that's how it helps brain function. But the negative part of that is that if you already have a glutamate issue, you might not need to have that type of upregulation, because overactivation of NMDA receptors can damage the GABA synapses and the glycine inhibitory synapses. So the compound that does that the most is S-sulfocysteine, and that's a byproduct of having sulfite oxidase or molybdenum cofactor deficiency. So I suggest definitely getting your SSC levels checked before you use benfotiamine, because you wouldn't want to increase your NMDA receptors if the SSC is overactivating them. That would just be really bad. It would be a bad situation. You would have a lot more receptors and a lot more activation of them, and that could hurt you. So be careful with benfotiamine. So moving on to B12. B12 can be a mopper upper, but it's specifically the hydroxycobalamin form. And to really mop up sulfite, you would have to inject super physiological levels of this form of B12. But you should know that there's also a risk of mopping up hydrogen sulfide, which is fine if you have too much. For example, in Down syndrome, there would be too much hydrogen sulfide. And so that might be something that you would want to do. But it also would mop up nitric oxide, and it can remove cyanide too. But nitric oxide is a Goldilocks gasotransmitter. We need some, but we need to not have too much. So in our diet, if you're consuming sulfites from wine or dried fruits, pickles, sausages, just check the labels, because the sulfite can directly bind to the B12 that's in food, and there is actually hydroxycobalamin in our food supply. So I would check food labels for that, because it could be causing a B12 deficiency. And then we also have to think about where this is from another presentation that I'm about to do, making molybdenum cofactor. And one of the things that can go wrong is you don't make enough S-adenosylmethionine, or SAM. And this B12 issue could be related to how sulfite can increase lysosomal membrane permeability. So B12 is metabolized in lysosomes. So let's look at this diagram. So we have transcobalamin, and transcobalamin holds on to B12. So here's the cobalamin. And then it will connect with a transcobalamin receptor, and then the cell it engulfs it into a lysosome. And then the lysosome is where you process the B12, and you can remove the cobalamin, and then you remove it from the transcobalamin, and then it's released and used in these cofactors in the cell. So sulfite can actually cause lysosomes to become leaky because of oxidative stress, and that could release the B12. And then that B12, if you have intracellular sulfite, could be destroyed. So anyone who has sulfite oxidase deficiency or Moco deficiency, or increased CDO activity because the hypoxia pathway is increased, maybe they do have that B1 deficiency that happened outside of the cell, they're at risk for having intracellular B12 deficiency. Okay, because sulfite can bind to cobalamin when it's not in its methyl form or its cyanocobalamin form, which I don't recommend that form of B12, by the way. And then obviously it can bind to the hydroxycobalamin, and it can bind to adenosylcobalamin once that particular component is removed. So yeah, I think something else about lysosomes is that if you have Lyme's disease, that bacteria has been shown to cause lysosomes to explode and empty their contents outside of the cell. So that's another issue. Let's see. Now we're going to talk about betaine. So sulfite can actually bind to the precursor for betaine, which is betaine aldehyde, making a sulfobetaine. So let's look at that. I should show you what it looked like. Sorry. Here's the sulfobetaine. You can see the sulfite. It binds to the aldehyde group. Okay, so it can alter the availability of betaine, and betaine is super important because it runs methionine salvage, where you convert homocysteine to methionine when there's not enough B12 or 5-methylfolate to be able to work that reaction in the liver and the kidneys, and also in a small portion of the brain, specifically oligodendrocytes will use betaine. When they're actually under oxidative stress, they start to use betaine, and they need that to be able to make myelin. So super important. In fact, they see in MS that the betaine levels are not high enough to be able to maintain the myelin sheath. So that's quite interesting. So before you make betaine, you're actually making betaine aldehyde from choline. And this enzyme right here, choline dehydrogenase, it actually has FAD as its cofactor, and sulfite can bind to the N5 position on FAD, but there's not kinetic studies on this. It's just a highly possible inhibition of this enzyme because of the way that the sulfite binds to a catalytic region of FAD. So it could be that you actually don't make much betaine aldehyde, but we know for sure that sulfite can bind to betaine aldehyde, and that overall can reduce your betaine intake. So those with mitochondrial sulfite toxicity are at risk for betaine deficiency. This happens inside of the mitochondrial membrane. It's not happening. The conversion of choline to betaine is not happening in the cytosol. So it's in the intermembrane space. So that's important to remember. So this has to be mitochondrial sulfite toxicity. And sulfite won't bind to betaine. It doesn't have an aldehyde group, so it won't bind to betaine. So then ALDH7A1 is one of the enzymes that can make betaine, and I don't have shown here, but there's another one. It's ALDH9A1. So again, though, you could have the sulfite binding right here to betaine aldehyde, and then that could cause a betaine deficiency. And the ALDH7A1 is like it's a moonlighting enzyme, and it's the very original theory that Jenny and I worked on to explain my own daughter's health issues and her late onset seizure disorder. So what we think was going on is that sulfite was inhibiting ALDH7A1 in all of these pathways that it can participate in. And so it can decrease when ALDH7A1 is decreased. Then there's actually a buildup of these lipid peroxides. So having high lipid peroxides could be a marker for sulfite toxicity in sulfite inhibiting ALDH7A1. The backup for that is ALDH1A1, which is it's the low dose, high affinity metabolizer of vitamin A, of retinol aldehyde. And so we came up with this theory that as the serum vitamin A levels are going up, because if you have a buildup of retinol aldehyde, it can be converted back to retinol. And so then overall your retinol levels would go up. And so as vitamin A was going up in serum for Jenny, she was experiencing this inability to get rid of lipid peroxides. And so we think that the lipid peroxides were being metabolized by her ALDH1A1, which should have been metabolizing her vitamin A in the liver, if that makes any sense. So that's pretty interesting connection. Sulfite can also inhibit this ALDH7A1 here. I think that there's more ALDH enzymes that can deal with the I can't say that one, imidazoles acetaldehyde. That's part of the histamine pathway. Um, so it's possible that it's another one, but it could be contributing to excess histamine having to go through HNMT, and that requires SAM. So ALDH7A1 is also involved in lysine metabolism. And if this is inhibited by sulfite, then there's a buildup of AASA, and that isomerizes to P6C. And P6C will bind to your active form of B6, P5P, and inactivate it. And so Jenny had late onset seizure disorder, and it makes sense that for her, it was it was related to ALDH7A1. She believes that she had low B6 levels, and that contributed to high glutamate levels in her brain. And then we realized that sulfite in the form of SSC could actually be like glutamate on steroids. And so it was also a contributing factor. So it all comes back to, though, her another theory that she had, which is the Moco steel. And that's what our sulfite toxicity group was originally started for. And it's just progressed over time, where we're finding all these different ways that you can have altered sulfur metabolism or sulfite metabolism. Okay, so it's pretty cool. The other, if you look for the video on the Moco steel, it'll explain more about that. So as you can see, that the whole betaine pathway is kind of interconnected because of the ALDH7A1. And sulfite, though, also can form a sulfonate with P5P, but this is reversible. So as the levels of sulfite go down, wherever this P5P is, or the pyridoxal form of B6 is, it will actually come off of the B6. So not every form of B6 found in our diet has phosphate added to it, because remember I was talking about the enzyme alkaline phosphatase. That enzyme can metabolize benfotiamine so that you can absorb it. It also metabolizes lipopolysaccharide, especially when you don't have enough secretory IgA to deal with your lipopolysaccharide. I need to do an entire presentation about that. And I think I already said that. I've been recording this in little increments between taking care of my daughter. So, some forms, though, require alkaline phosphatase. Specifically, supplements of P5P are going to require alkaline phosphatase because you have to remove a phosphate group from the pyridoxal form of B6 for it to enter the cell. So the same thing if you were to take a form that says PNP or PMP, but usually you don't see that. You usually see on supplements that there's pyridoxine or there's P5P, and then there's actually pyridoxamine hydrochloride, but something kind of interesting happened with that. In 2009, it was labeled a new drug, and now it's not available as a supplement. But it's also not available as a drug, except in Australia. It's like a controlled substance. So that's kind of interesting. So we have all these different forms of B6, and the only one that sulfite binds to is the pyridoxal phosphate form, or the pyridoxal form. So it's possible that if you're eating sulfite containing animal foods in some plants, but if let's say you're eating sausage, that's like your main food, and you eat sausage with sulfite in it, well, definitely that pyridoxal form of B6 is not available. It's probably got sulfite bound to it. So again, pyridoxal forms of B6 can have sulfite covalently bound to the aldehyde group, and that produces a sulfonate. But when sulfite levels go down, then the sulfite will come off of that aldehyde group, and that B6 would be available again. And the predominant form of B6 that's in our blood is actually the pyridoxal phosphate form. It's bound to albumin. And while it's on albumin, the aldehyde is protected. The problem occurs when we get into acidosis. And during acidosis, the PLP can come off of albumin. It's also called P5P, but it can come off of albumin and then it can be exposed to sulfite that's in the blood. And that's when the sulfite can interact with the B6. And at that point, alkaline phosphatase that's in the tissues, in the peripheral tissues, may not be able to uptake that form of B6, might not recognize it as well. So that's a possibility. So we do have a B6 salvage pathway, like I was saying, and that makes it a very crucial vitamin. When there's a pathway designed into us to keep a vitamin recirculating, you know that it's important. Can you accumulate pyridoxine and get excessive amounts of that? And can that cause B6 toxicity? I think it potentially can, but why would it do that? It probably is because you're struggling with molybdenum cofactor, because the enzyme to convert pyridoxal form of B6 to pyridoxic acid in the liver is aldehyde oxidase, and that's a molybdenum cofactor dependent enzyme. And so you can actually see pyridoxic acid on an organic acid test. And when this is low, often the results section will say, this person, they must have a B6 deficiency. But in actuality, you could have B6 deficiency, but you could have a molybdenum cofactor deficiency. One way to know if you have a molybdenum cofactor deficiency is if you do not have very much uric acid, because uric acid is made by xanthine oxidase and xanthine dehydrogenase, and that requires molybdenum cofactor. So another possibility that can happen whenever you're struggling with sulfite is you can have excess hydroxyl radicals that can activate B6. And I'll show that here in a minute. But I wanted to talk to you about the risk for developing B6 toxicity. And there's a group, the B6 toxicity support group on Facebook. And the big hypothesis that they have, and it's a really good hypothesis, that the problem is very high doses of B6, any form, and then a dehydration event that causes concentrations of metals in the body. So if you have a dehydration event, it can concentrate zinc, and very high doses of zinc can inhibit the pyridoxal kinase enzyme. So very low doses of zinc ATP can act as a cofactor, but very high doses of zinc ATP can actually act as an inhibitor, because the natural best cofactor is magnesium ATP. So yeah, you could see like maybe if the cell became super concentrated because someone is dehydrated, then this enzyme would not work well. And then the pyridoxal form of B6 will build up. And then that can be excreted. If there's enough Moco, you can turn it into pyridoxic acid. But if you don't have enough Moco for aldehyde oxidase, then you're going to reduce this pyridoxal via pyridoxal reductase to pyridoxine. And the pyridoxine is what has been implicated in causing neuropathy. So it is possible to have this happen. So then the question would be, should we even supplement with B6? Is the risk too great? And I'm thinking that if you are struggling with B6 and you have evidence of intracellular B6 deficiency, then I think it's detrimental to withhold something that could be helpful. B6 is super vulnerable to oxidative stress, and I'll show you the hydroxyl radical thing here in a minute. So the question is your high blood B6 level actually saying that you're toxic because you're getting all the symptoms of B6 toxicity from it being high in your blood. But what if it's actually B6 deficiency? Without someone doing like a biopsy of your nerves, how would you even know if it's pyridoxine in there? I don't think you would know. So anyway, I don't know if that will be accepted by most people. So I think that we should use supplements with caution. I think that I myself was concerned about my very high blood B6 levels. I did a whole video on it. And then I only supplemented with 5 milligrams of P5P for over 2 years. And I didn't get better, I got worse. And I think that it was because, and I know it was because I got a B6 deficiency because I did a plasma amino acid test and my cystathionine levels were high. And I had all the signs of glutamate dysregulation and neuropathy. And I think that I was not out competing the oxidative stress in my body. So that's just me. Maybe somebody else is feeling the same thing. So again, there's a couple ironies going on. B6 is the form of P5P that is also essential for modifying the molybdenum cofactor to be used for aldehyde oxidase. So if you don't get in enough B6, then you won't be able to metabolize away and accumulated pyridoxal forms of B6. And then B6 is the form of P5P that is needed for making iron-sulfur clusters that you use to make Moco. So if you don't get in enough B6 and have enough active B6 that's not been, inactivated by sulfite or inactivated by hydroxyl radicals, then you're not going to be able to make molybdenum cofactor, and things are only going to get worse. So something to think about, and I already said it, but the safest form of supplements would be pyridoxamine. So if you look, when you absorb the pyridoxamine into your cell and you activate it to pyridoxal kinase, and then you have pyridoxamine 5-phosphate, and that can be converted to pyridoxal 5-phosphate, then it's like a long, drawn out way to get back to pyridoxal, right? And so the likelihood that it's going to accumulate as this pyridoxal form of B6 is minimal. And it was made a new drug in 2009. And so now it's not available, except for in Australia, it's available as a pharmacist only medicine category. But Europe and US have no access to it. It's been shown to reduce hydroxyl radicals and decrease inflammation. So, okay, so not sure why I have that there. Oh, I was going to talk about this. I just didn't highlight it. Okay, so salvageable cysteine or dead end complexes are other ways that we can deal with sulfite. So if you have excess sulfite, then normally you're going to use sulfite oxidase that uses molybdenum cofactor to make sulfate. That's the normal process. However, if that doesn't happen, then when sulfite starts to accumulate, you can use glutathione. Or if most of your sulfite is coming from the CDO enzyme, then that sulfite could be complexed with glutathione to make a sulfonate. And then the sulfonate leaves via this MRP1. It's called multi-drug resistant associated protein 1. It leaves and it's metabolized by GGT. And then GGT will remove the glutamate, and then you just have cysteine and glycine bound to sulfite. And then a dipeptidase is going to remove the glycine. And then what you have left is S-sulfocysteine. S-sulfocysteine is cysteine plus sulfide. So this is one way that our bodies will make S-sulfocysteine. But it's not the only way, because if you have cysteine floating around in your blood, then you can convert cysteine plus sulfite into S-sulfocysteine. Okay, so, but the levels would have to be super high to make S-sulfocysteine in your blood. And this would be more likely to occur during alkalosis than in acidosis. That's just what the studies show. So SSC can actually be used as a source of cysteine. It can enter through the XC transporter, and to enter in here, then glutamate has to leave. So once the SSC gets inside of the cell, a glutathione is going to help to make S-sulfocysteine glutathione, and then glutaroredoxin will convert it to cysteine and sulfite, and then the sulfite should move along to the mitochondria and be detoxified by sulfite oxidase. The problem that happens is when you don't have sulfite oxidase, you don't have that endgame enzyme, you can't finish this process and make sulfate. And so then the sulfite continues to accumulate until you do not have enough glutathione to use S-sulfocysteine anymore. And then on top of that, some of the things that glutathione causes, like glutathione, sorry, not glutathione causes. Some of the things that sulfite can do is sulfite can inhibit glutathione reductase. And so that prevents you from recycling glutathione. So high intracellular sulfite levels from sulfite oxidase deficiency is a severe issue. I mean, this is not a good situation at all because you're going to struggle badly with recycling glutathione. So yeah, you're going to end up with some dead end products, right? You'll have too much S-sulfocysteine and too much or too little glutathione. Okay, so now we can see that sulfite causes a large amount of nutrient deficiencies. If that sulfite is happening right there in the portal vein, right where all the LPS is and all of the FMLP from bacteria is overexciting the neutrophils, then that actually would lead to more sulfite and then problems with all these cofactors. So there was a study done on the effects of sulfite on macrophage function in normal and sulfite oxidase deficient rats. And what they found was that having sulfite oxidase deficiency increases the phagocytic and chemotactic activity of macrophages in the peritoneum. So they become more active, way more active macrophages when there's sulfite laying around. So anyone who has very high levels of S-sulfocysteine, you would be considered someone who has sulfite oxidase deficiency, whether that's because you're not making enough heme to finish the sulfite oxidase enzyme, or maybe you struggle with making molybdenum cofactor despite consuming molybdenum, which that can happen. If you have this going on, your macrophages are angry, like super angry. And in these rats, they went ahead and gave them 50 milligrams per kilogram of vitamin E. And they figured out that the vitamin E helped to slow down the effects of having sulfite oxidase deficiency on macrophages. And they hypothesized that it's related to reactive oxygen species. So most likely the vitamin E was helping to recycle vitamin C, probably. That's what I'm thinking. And then the vitamin C was helping to mitigate the hydroxyl radicals. That's my theory, at least. So if you're a human, the dosing of that would be 486 milligrams for a 60 kilogram adult. The upper limit for vitamin E is 300 milligrams per day in Europe. And in the US, we give a generous 1,000 milligrams per day. The RDA is 15 milligrams. So high dose vitamin E can be problematic because it can act as a pro-oxidant. If you take too much, sometimes things that are antioxidants become pro-oxidant. The same thing with vitamin C. Taking too much vitamin C can cause oxidative stress by being metabolized to hydrogen peroxide. And then it can also produce oxalate. So yeah, and oxalates, if you make an oxalate crystal, then it aggravates neutrophils when they're big. The neutrophils will try to engulf it and phagocyte it, like go through phagocytosis. But because they get frustrated, they spill out their contents. It's called frustrated phagosomes. And so there's more oxidative stress when you have oxalic acid crystals in your blood or in your kidneys. It makes all this nasty, frustrated phagocytes kind of creepy. Anyway, so that can happen if you're a person who makes kidney stones. You might have frustrated phagocytes. I'm sorry. So, what if you don't have sulfite oxidase deficiency levels of oxidative stress? Would this high dose vitamin E actually be a pro-oxidant? That's one good question. And what if you are sulfite toxic, but you're toxic outside of the mitochondria? And more specifically, you're not toxic inside of cells, you're toxic in the plasma with sulfite. Would you need that much vitamin E? I'm not sure. I do think we need vitamin E. So if you have a vitamin E deficient diet, you need to monitor that and see if you can get more vitamin E in. So sulfite can aggravate those macrophages, and sulfite activates an ADPH oxidase or NOx, and that can lead to increased superoxide. And these macrophages produce nitric oxide using inducible nitric oxide synthase, or what we call iNOS. It's also called NOS2, and that produces nitric oxide. And that nitric oxide becomes toxic to the cell when it combines with superoxide. So it's super important to have a working superoxide dismutase. So let's say that this superoxide is actually in the extracellular space. So that superoxide dismutase at that point will require copper. SOD that's in the cytosol, it requires zinc and copper. And then SOD that's in the mitochondria is going to require manganese as its cofactor. So anyone with a copper deficiency is at a high risk of struggling with the nitric oxide that's floating around in the blood freely, that's a gasotransmitter that's being released by macrophages, and then also superoxide that floats freely around in plasma. Those two things can combine and produce peroxynitrate. And peroxynitrate is mostly protonated to this protonated form at a physiological pH, and then it will isomerize into nitrate, and then it can also become this nitrite radical and hydroxyl radical. Okay, then in the presence of CO2, it can become this toxic peroxynitrite carbonate, and that is cytotoxic. And it's also antimicrobial, so that's why macrophages would want to produce that, as to help kill off whatever they're encountering. Okay, it's a defense system. Now, your macrophage itself should have its own antioxidant system, and so that it's not hurting its own self, right? But again, these things can be released. The nitric oxide can be released into the extracellular space, as well as can the superoxide. And so if you do not have, like if your cells do not have enough glutathione to be able to deal with the excess peroxynitrate, it's going to accumulate, and it can produce hydroxyl radicals. So this particular compound, peroxynitrate carbonate, it's also implicated in atherosclerosis and neurodegenerative disease and chronic inflammatory disorders. So there's other ways that we can produce hydroxyl radicals. It's not just those angry macrophages that are extra stimulated by sulfite. It also can be from the Fenton reaction. And that is where hydrogen peroxide can interact with ferric iron. So definitely excess peroxynitrate can lead to hydroxyl radicals. So we know that those can come from the activation of macrophages. But this can also occur because of the Fenton reaction. So hydrogen peroxide can react with ferrous iron to form ferric iron and hydroxyl radicals. That's one possible step. And then hydrogen peroxide can react with ferric forms of iron, ferric iron, and produce ferrous iron and hydrogen ions in this hydroperoxyl group. And then superoxide can actually interact with ferric iron and it produces the ferrous iron that can then interact with hydrogen peroxide. So you can see like we got a lot of stuff going on here. So superoxide can contribute in a roundabout way to producing hydroxyl radicals all on its own without having to be converted to peroxynitrate is what I wanted to show here. And so if you have a struggle with controlling cellular iron levels or blood iron levels, you have a risk for making these hydroxyl radicals. So how do we deal with the constituents that encourage the Fenton reaction? Well, you have to have catalase that metabolizes hydrogen peroxide to water and oxygen, and that's heme dependent. And iron is what you need partly to make heme. It's a multi-step process to make heme, and you also would require B6 for this. So if you are B6 deficient, which ironically, I'll show you in a bit, hydroxyl radicals could do that, then you won't be able to make enough heme to run catalase. So then the glutathione peroxidase, it metabolizes hydrogen peroxide as well, and it requires selenium and glutathione. So making sure that you get enough dietary selenium is quite important for that. And in a glutathione deficient state, you're going to obviously struggle with dealing with hydrogen peroxide. So even with these enzymes in place, the Fenton reaction still can occur when iron isn't handled right. So I'm going to show you how sulfites can alter lysosomes and contribute to this issue. And then also if you have a problem with ferritin, for example, I had one client who had hemochromatosis and was taking very high dose vitamin D, which was pushing down ferritin even more, which allows iron to be more free in the blood. And so that can cause the Fenton reaction in the blood when there's too much unbound iron. So avoiding very, very high dose vitamin D supplements would be helpful. And then if you have ferritin light chain or heavy chain disorders, that could contribute to this because it means you're not binding iron very well in cells. And then hemochromatosis would obviously be an issue too, because that's a state of iron overload. So another enzyme that is quite helpful for dealing with superoxide, but it does produce hydrogen peroxide, is superoxide dismutase. And I've said this previously that there's 3 isoforms. So the copper zinc form is SOD1 and it's cytosolic. And then magnesium is the cofactor for the mitochondrial superoxide dismutase. And then the extracellular superoxide dismutase requires copper. So individuals with copper deficiency are going to struggle with excess superoxide, but also when you have copper deficiency, you tend to have lower ceruloplasmin levels, and you require ceruloplasmin to be able to put copper safely onto transferrin. When cells are exposed to excess sulfite, it increases reactive oxygen species, and it can cause these lysosomes that carry iron to release iron into the cytosol, where it can cause the Fenton reaction. Remember, that is ferrous iron plus hydrogen peroxide produces ferric iron in hydroxyl radicals. So they did this study with sodium sulfite, and it triggered the liver cells, the hepatocytes, to go through ferroptosis. And they proved that it was related to the mitochondrial reactive oxygen species triggering the lysosomes to release iron by blocking the mitochondrial reactive oxygen species, and then also by stabilizing the lysosomes with mannose. Although we can't do that with dietary mannose, it doesn't work like that. So I was like, ooh, that's cool, but you can't actually take mannose and stabilize your lysosomes in that way. This is a cell model, so they just squirt it in there. So we can't do that. We can't determine exactly where it goes. But they did use a lysosomal iron chelator, and that also stopped the Fenton reaction. But without these interventions, then the cell ended up with lipid peroxides, and it went through ferroptosis. And they found the same type of lysosomal the background sounds. The lysosomal cell death can happen when a cell is exposed to lipopolysaccharide. So when liver cells are exposed to lipopolysaccharide, they also go through this same problem with the lysosomes breaking open. And then remember that in Lyme's disease, that bacteria can increase lysosome fragility as well. So that's something to consider, that we all could be at risk for these excessive hydroxyl radicals when we're dealing with LPS or when we're dealing with sulfite in excess. So the researchers that were talking about, the polarized macrophages, they feel that nitric oxide could actually break the lipid peroxide chain reaction, because once you start making lipid peroxides, it's hard to stop the chain reaction. It just keeps going and going until all of the phospholipids in a membrane have lipid peroxides. And so they feel that nitric oxide can terminate this, and they proved it. The issue then is not nitric oxide. And this was an interesting lesson for me to learn, because I just want to shut off the nitric oxide. Like I myself, I know my own genetics and my own health history, and I have a high iNOS state. I'll just be honest. And if you're in our support group, you know my weirdness. And so I would like to blame some of my downfall on the fact that I thought that I was accumulating vitamin A. And so I reduced my vitamin A intake, and I was never a big vitamin A eater anyway. But I cut out beta carotene and I went downhill. So, I do have some beta carotene monooxygenase SNPs, but I'm not a knockout mouse. I can convert beta carotene to vitamin A, but I really don't like vitamin A foods that much. I'm not a big fan of cheese or butter, or we eat salmon, but not very often. So my vitamin A intake plummeted for about 6 months. And this was when my own daughter had very high serum vitamin A levels. And I went on a big deep dive about vitamin A over the past 3 years. And she was not vitamin A toxic. I would just like to say that. And her serum vitamin A was likely elevated because of calcium dysregulation. That's my number one theory on that. So, and then also she struggles with NAD. She does not make enough NAD. Her kynurenine pathway sucks. And so she just needed to do better in that way as well. So anyway, I digress. Now you know more about me. So let's talk about those hydroxyl radicals. So we already know that sulfite can reversibly interact with the pyridoxal form of B6, but also over here, they showed that vitamin B6 can quench hydroxyl radicals. Do you see how many hydroxyl radicals can bind to B6? And so they proposed that pyridoxine, which pyridoxine is very similar to these other forms of B6, but it can quench up to 6 to 8 hydroxyl radicals at a time. So RB6 is being extremely modified by hydroxyl radicals. That's my opinion of it. And I think it's a very vulnerable vitamin. We do have a salvage pathway for it, showing that it's essential. Just because the active form is an aldehyde doesn't mean that it's a toxic aldehyde. We definitely require it. And hydroxyl radicals are our insane enemy. And B6 is something that I see over and over again when I'm helping people, that they're vulnerable. This B6 molecule is vulnerable. So this slide is just sharing with you that all forms of B6 are capable of mopping up hydroxyl radicals. So at that point, it's not available for use in an enzyme, but I mean, obviously P5P is the active form, and it can act as a potent antioxidant, and it reacts with hydroxyl radicals. So super vulnerable B6, right? And then this pyridoxamine form has been proven in studies to be the most effective antioxidant form of B6. And again, it's now a drug that's not available. So, yeah. So the excess nitric oxide from iNOS is what the researchers who studied these M1 polarized macrophages think that could save us from lipid peroxides and worsening ferroptosis. But it can't, is what I'm trying to say there. The excess peroxynitrate is the big issue here. And in theory, you would want to avoid things that inhibit nitric oxide or iNOS, in theory, based on this particular presentation, because they're saying that that nitric oxide that's being provided can stop the lipid peroxidations. So you need to deal with the excess production of the peroxynitrate and the hydroxyl radicals in the superoxide. Those are the things that need to be dealt with. The hydroxyl radical might be the biggest problem contributing to sulfite oxidase deficiency or Moco deficiency. And then you have a feed-forward effect, because then you're going to have more sulfite. So to make molybdenum cofactor, and I promise I am going to make a whole video on this, but a lot of the research that I did for how sulfite affects these micronutrients in the body actually works into this particular next presentation. So there are several steps to making Moco, and they're compartmentalized between the cytosol and the mitochondria. So I'll be looking at that in the next video, but this is just an overview of making molybdenum cofactor. And you have to be able to make this CMP right here from GTP, you need SAM, but not just SAM, which to make this radical SAM, you require iron-sulfur clusters. And iron-sulfur clusters require iron, but also B6 is needed to make that. And then the methionine salvage pathway, we would hope that it's working well. You can still make SAM just from methionine, but hydroxyl radicals can actually damage this part too. And I'll show you that. I have a slide. So making SAM is not dependent on B12 and 5-methylfolate or betaine, but salvaging methionine so that there's enough to be able to make SAM needs these particular cofactors. And we saw that B12 can be vulnerable, especially if the lysosomes are leaking from sulfite. Then the sulfite can bind to the B12 intracellularly. We know that sulfite in the diet can bind to B12. Methylfolate or folate in general is very subjective to oxidative stress. So that's a problem. And then the enzyme serine hydroxymethyltransferase is B6 dependent, and that helps you to make the precursor for 5-methylfolate. So if you're low on B6, you're going to struggle with making what 5-methylfolate comes from. It's I think it's 5,10-methyl tetrahydrofolate. 5,10, yeah. And then again, betaine aldehyde is compromised, or betaine is, because betaine aldehyde can be bound to sulfite. So already in this very first step, you're compromised. Okay. Another component that you need to know is that if you have S-sulfocysteine, that itself can cause a cysteine deficient state. And this sulfur molecule right here that is needed for the next step, these two enzymes, that comes from cysteine. Okay, so it requires the assembly of MPT synthase for CPM to MPT. So that's this synthase molecule. It actually requires cysteine and magnesium, and then zinc stabilizes this enzyme complex. And then the addition of molybdate is via gefrin. Gefrin serves as a scaffold to hold GABA synapses and glycine synapses in place. And we know that SSC in the brain causes high intracellular calcium levels, and that destroys gefrin by activating calpain protease. Calpain protease will break down gefrin. However, there aren't studies on high intracellular calcium directly affecting gefrin outside of the brain. So I'm not sure if it would, like if you had high intracellular calcium levels in your kidneys or your liver, would that destroy gefrin also? That's something that needs to be studied. So this step requires ATP and magnesium, and then a tiny bit of copper too. So if you're struggling with copper deficiency, that could be a problem. But then on Sergey's website, I saw a bit about if you have very high copper levels, that could also cause a problem with making molybdenum cofactor. So we don't want to go super high either. So here's the reaction where you actually need iron-sulfur clusters for radical SAM enzyme activity, and being able to make iron-sulfur clusters is dependent on this enzyme cysteine desulfurase. And so it mobilizes the sulfur from cysteine, and that's B6 dependent. And these are the other genes involved in making sulfur clusters. And so you could have a genetic problem. And these are the things you would want to look up on a genetic test. Sergey has a program called Gene Inspector Pro that looks at all of these different types of genes and looks for the things that are wrong, that are the very rare polymorphisms that sometimes would be overlooked, because if there's not massive information on these very rare variants, then they're not always listed in like a gene database. So once you are making Moco, the Moco is added. So Moco, kind of the production of it goes in and out, and I'll talk about that in the next video. But once you've made it, then you actually have to load the Moco onto this enzyme. This is called the pre-sulfite oxidase enzyme. And that enzyme comes in here through this thing called Tom complex. And then you have to load the Moco, and then you have to add heme. And heme is, to make heme, that's a multi-step process that will be for another video. And it does require B6 in the first step. So if you are struggling with heme synthesis, then you are going to struggle with making sulfite oxidase. Now, there is triage. Our bodies like to triage. So I would hope that we conserve heme for this very important enzyme because, again, it's protecting the mitochondria from sulfite toxicity. So how can we mop up that crappy hydroxyl radical? You could increase your flavonoids. So they will scavenge hydroxyl radicals, but then at high doses, like if you're taking pill supplement forms of flavonoids, then it can interfere with normal redox signaling. It can also mess with your drug metabolism. So I would be careful with that. But it wouldn't hurt to do some type of like high flavonoid tea. I'm super into hibiscus tea right now because once you've been struggling with peroxynitrate and hydroxyl radicals for a long time, you'll get endothelial dysfunction. And then you'll go from someone who used to have really low blood pressure from POTS to super high blood pressure from endothelial dysfunction. That's pretty crazy to go from chronically low blood pressure to these spikes in blood pressure. Or it may just be studying sulfite toxicity that's making my blood pressure higher. So these are beta carboline alkaloids. I am not sure where you would find that, to be honest. So I don't think I would be reaching out for those. This is also like anthocyanidins. They're probably in food, but if you're eating foods that have antioxidants, it's safe, but I would not take high doses of these particular things. So then vitamin E, it can deal with lipid peroxides and some hydroxyl radicals, but at high doses, it can be a pro-oxidant and it can cause hemorrhages. And like you can bleed out it can cause platelets to not aggregate. So if you have very low platelet levels, this could be an issue. Something that can happen if you have iron deficiency and then you start to replete the iron, you can have a reactive drop in your platelets. So be aware of that. It does happen. And so there's a moment in time where you could have very low platelet levels. Vitamin C is good at scavenging hydroxyl radicals, but then at high doses, it can become a pro-oxidant. And then I talked about how it can actually produce some hydrogen peroxide and oxalate. So sometimes it can increase the risk of kidney stones. And for people with hemochromatosis, it can increase your iron absorption, and that can lead to worsening iron status, like an iron overload state. And then my favorite one is molecular hydrogen, because it doesn't just mop up hydroxyl radicals, it also mops up peroxynitrate. And that is the perfect thing, because that's what we've been talking about is excessive hydroxyl radicals and peroxynitrate causing a lot of the problems, right? So does it disrupt redox homeostasis? The studies show that it doesn't. It selectively scavenges hydroxyl radicals and peroxynitrates, and it does not scavenge nitric oxide. Sorry, that's a typo right there. It doesn't affect nitric oxide at all. It just deals with the hydroxyl radicals and peroxynitrate. And oh no, it's not a typo. I see it now. It says does not. And then there's no evidence of redox imbalance or adverse effects with therapeutic use. It can activate the NRF2 pathway, but it doesn't prolong activation of it. And so I've been reading and listening to information about this. And one thing I do recommend, though, is I do not recommend if you are a fragile person, I do not recommend taking molecular hydrogen water before you exercise. Likely you're not exercising anyway. Most of the people that contact me are like, I don't exercise, I can't. But if you take it before you exercise, then it can increase your oxidative stress and you should recover faster from that. But if you're already experiencing oxidative stress, I don't think it would be wise to push your body to be able to have more oxidative stress. And how it most likely works is that when you drink hydrogen water before your workout, it gives you like a boost in being able to work out harder. So that's where the oxidative stress seems to be coming from. But then studies show that you recover faster after that. So I suggest, just using it on an empty stomach and using hydrogen tablets that are third-party tested. And I looked into hydrogen water bottles, and even though it would save money in the long run, it's very inconsistent how much hydrogen, molecular hydrogen, would be produced. So I'm also looked into the Inhale 2 machine that's coming out as a way to deliver hydrogen, molecular hydrogen as gas, because we do have some asthma in our family, as well as Zoe has sleep apnea. And I was reading how the hydrogen gas can help with the oxidative stress that's occurring in the brain due to intermittent hypoxia. And we do our best to try to keep her CPAP on, but she doesn't even wear it for 4 hours a night. So there's some serious oxidative stress going on there. So one more thing to talk about, why I keep harping on the hydroxyl radicals. So hydroxyl radicals can inhibit methionine adenosyl transferase, or MAT. MAT is the enzyme that converts methionine to SAM. And I've seen a couple people with high methionine levels, and often that is considered that it's a CBS deficiency. So you're just driving your your homocysteine towards methionine because you have a block at CBS, which could be a severe B6 deficiency, but typically you would just see high cystathionine levels in a severe B6 deficiency. But what I think could be going on for many people is that they have these excess hydroxyl radicals, and those are inhibitors of MAT. And then they don't have enough SAM to be able to make radical SAM. And then that leads to the inability to do many methylation reactions. And then that will lead also to lack of radical SAM to be able to make molybdenum cofactor and more sulfite. And then the more sulfite will trigger more hydroxyl radicals, right? Because it'll, at minimum inside the cell, it will cause the lysosomes to leak. And then the lysosomes leaking will leak iron into the cell, and then the iron will cause the Fenton reaction, and then you have hydroxyl radicals. So it's a big issue. We need to mop these guys up. And then MAT can be inhibited by S-nitrosylated glutathione, but this is like a physiological inhibition that kind of comes and goes. It's not like an insane toxic inhibition. And this can be reversed by glutathione, but glutathione can be tied up in sulfite metabolism. So if you truly have sulfite oxidase deficiency, we truly need these hydroxyl radicals to go the heck away, right? So it is not just me who thinks this is a problem. Bob Miller and Dr. Jill Carnahan, they studied NOx in depth. And I love Bob Miller's idea that it's an underwater chess game, because seriously, this is an underwater chess game. So they both talk about using hydrogen water to deal with the hydroxyl radicals. And then I found this study showing that the hydrogen water, they use this a way of making it with like electric, right? But there's studies where it's just hydrogen water made with hydrogen water tablets, which are magnesium that it in a bunch of like organic acids that cause a reaction that displaces the hydrogen from the water so that the hydrogen is more free inside the water. And those were developed by Alex Tenarva with the help of Dr. Tyler LeBaron as like a consultant. And so he created this hydrogen tablet, and now, years later, he sold the company that made it, and it's the brand Rejuvenate. And now he just studies hydrogen water. And then he and Dr. Tyler LeBaron, for the past 7 years, have been trying to develop the Inhale 2, which is a device that produces hydrogen gas, but very tightly controlled, so that they're able to use it for studies to be able to titrate the amounts of molecular hydrogen that are needed for specific disease states. And so they've made this piece of equipment and they're selling it to the public and to clinics. So it just started coming out in October, and you have to pre-order it. Sorry about my dog barking. I hope that's not super annoying. She's bothering me. So I think the hydrogen tablets are probably a better, after, listening to a lot of things in reading, I think that the hydrogen tablets would be better than a hydrogen water bottle just because of consistency and delivery of the molecular hydrogen. So again, it can deal with the hydroxyl radicals in the peroxynitrate, and they believe that it's going to help with all kinds of disease states like arthritis, cancer, diabetes, and inflammatory bowel disease. So there's a lot of good studies on that. So it's not just the hydroxyl radical that's damaging individuals that have excess sulfite, though. So sulfite and peroxynitrate and the hydroxyl radicals all can inhibit glutathione peroxidase and glutathione-s-transferase. So something that I just recently saw that was puzzling to me, and I've seen it on a few Genova tests in the past, is that people will have normal glutathione levels in their whole red blood cells, but then they have high lipid peroxides. And that just doesn't fly. That doesn't make sense. Why would you have high lipid peroxides, which here's the peroxide right here, if you have normal glutathione? You should be dealing with that peroxynitrate, right? You should not be going towards hydroxyl radicals. And that's concerning to me. We should be able to deal with that, like where the hydroxyl radicals are coming from. And then within the cells, the glutathione should also help, right? So it should help reduce the oxidative stress, but it's not doing that. And people are having lipid peroxide. So I wonder if the issue is actually that the sulfite or the peroxynitrate or even the hydroxyl radicals are in such large amounts that they're inhibiting the GPX from doing its reaction. So this person reached out to me, and that's when I started noticing that people can be having high glutathione levels in their whole blood, but then also very high lipid peroxides, and that just doesn't fly. That doesn't match up. And this particular person also had a plasma glutathione level checked, and you can see overall it's low. And then they have a higher marker of nitrotyrosine, which is a marker for peroxynitrate. Because when you have excess peroxynitrate, you start to nitrosylate tyrosine. And so this is quite interesting because it kind of fits with the idea that there's a lot of oxidative stress outside of the red blood cell. What could be causing that? And then you can see here, there's also this high nitric oxide levels. So this could be iNOS being induced, and it could be related to overactivation of the innate immune system. Although this person is super smart and a huge advocator and has come up with some other really good theories as well, such as that the peroxynitrate and hydroxyl radicals are shutting down the mitochondria, and so there's not as much CO2, and then that also would increase iNOS. I really like that theory. There's like a lot of things that could trigger inducible nitric oxide synthase. And then high ammonia levels could do something like that as well. And then this ammonia could be elevated because when you have excess hydroxy radicals destroying your B6, or let's just say sulfites even contributing to that, then you have a functional B6 deficiency, then you cannot produce enough ornithine to be able to keep the urea cycle going. And so that ammonia is going to build up. So this is pretty interesting. Yeah. So going back to this slide on the neutrophils, remember that the glutathione that is in our extracellular space, in our plasma and our blood, could be dealing with hypochlorous acid and also this sulfate and sulfite radicals. And these are irreversible glutathione adducts. And so that could be tanking the plasma glutathione, right? But whole blood glutathione is still okay. Now, whether or not this person has intracellular sulfite toxicity, the way to figure out if they did probably would just be OMX to see if they have high S-sulfocysteine levels, because that means once the sulfite has exceeded the capacity for sulfite oxidase, there's so much, the cells are just full of it, right? Okay, so I think that there's not just a tale of 2 sulfites. I think there's a tale of 3 sulfites. And so how would you know this? Well, the definitive answer is to get an OMX and look for S-sulfocysteine. Because if you have S-sulfocysteine, then you know that your SUOX Moco enzyme is not working if it's very high. And then if you don't have high S-sulfocysteine, but you still have symptoms of sulfite toxicity, then potentially it's your innate immune system producing all of the sulfite. And you could be an overachiever and you could be doing both, which is totally possible. And I believe that hanging out very long in this neutrophil dominant polarized macrophage state is going to lead you to an acquired sulfite oxidase Moco deficiency, because you're going to end up like with depletion of all of the cofactors required to make sulfite oxidase. So for example, you require SAM, right? And we talked about how to be able to make this radical SAM, you need iron-sulfur clusters. And to do that, you need B6. Well, hydroxyl radicals are screwing around with our B6. So there's that. And then to even have SAM, your MAT enzyme can be inhibited by hydroxyl radicals. So even if you consume methionine or you salvage methionine from homocysteine using betaine or B12 or 5-methylfolate, then you might not be able to work the MAT enzyme. And then betaine, again, you're going to have low levels of betaine because betaine aldehyde can form a covalent bond with sulfite. And so mitochondrial levels of betaine will be low as well. And that's where you produce it, right? So, and then again, if you have high S-sulfocysteine, or extra sulfite, that can bind to cysteine in the blood. Whether or not the S-sulfocysteine levels get high depends on how much sulfite there is, right? It's total amounts of sulfite going on. And then the other issue could be that you do need copper a tiny bit. On Sergey's website, there's actually a bit about excess copper he thinks could be damaging to making Moco, but we do need a small amount. And if you're constantly overworking your superoxide dismutase enzymes, you could develop a copper deficiency. Okay. And then there could be genetic components. And again, I think if you haven't seen Sergey's Gene Inspector, you can actually put your raw data into his program and you can find the very rare variants that probably aren't even in databases yet, but he has a great way of labeling them as potential problems based on their MAF score, which is how frequent these variants are in people, in the genome. And so if you have a very, very low MAF score, then it's a potential problem because if something is common, it doesn't kill people. That's a horrible way of saying it, but it's true. So, and kill as in making you feel really bad, not necessarily immediate death. Sometimes I wonder if humans were designed to suffer. We do have backdoor pathways, and everyone watching this video is likely using the backdoor pathways, but that doesn't mean they feel good. So, again, a tale of 3 sulfites. So if you have this problem, a sulfite oxidase deficiency, you're going to react to things that push your sulfur metabolism because you're going to end up with more sulfite. So garlic, sulfur foods, NAC, and glutathione supplements will all trigger sulfite toxicity symptoms. And then if you have innate immune system dominance, a lot of times we talk about using garlic to inhibit iNOS gene expression. But if you consume garlic, it increases hydrogen sulfide production by red blood cells. And then that's a gasotransmitter and it can leave your red blood cell. And then neutrophils can pick it up and produce sulfite. So, and an overachiever could do both of these things. Now we're going to talk about molybdenum. So, let me go back. It'll be easier to talk about it here. So if you have sulfite oxidase or Moco deficiency, you definitely want to supplement with molybdenum, but you also need to make sure that you're doing all the things, getting all the nutrients in that are depleted by sulfite so that you can have enough cofactors in place to be able to make Moco. There's multiple steps to making Moco. And then if doing all the things that are right doesn't work, then you might have a genetic issue, and that would be when you seek out genetic testing. GeneDx is a great place per Sergey to get your data done, because you can get your whole genome sequenced, and then you can get the raw data files, and then you can upload them into a software to analyze it. And I think his software is really well made. So if you do not incorporate your high dose molybdenum into Moco, then that molybdenum is toxic. There's no friendly way to put that. Molybdenum can cause cells to go through apoptosis. So you might, if you're this person and you have high SSC, you might benefit from high dose vitamin E like the rat study. I'm not saying that it won't be a pro-oxidant at some point, but it did rescue those rats. So that's something to consider. But of course, look at your platelet levels, see if you're at risk, maybe have a clotting study done. What is it? It's prothrombin time and INR, and see if those are normal before you take high dose vitamin E, just to be safe. And then something interesting can happen if you have iron deficiency. When you replete iron, you can have reactive thrombocytopenia, which means that your platelets will drop all of a sudden out of nowhere. So just be aware of that. That can happen to people. And so if you are increasing your iron and then you increase your vitamin E really high, but you happen to be in a low platelet state, it's possible to have a bleeding event. So caution, caution, caution. I know I'm not your healthcare practitioner, but I do care and I don't want to cause harm. So there's a lot of things to consider. Please talk with your own healthcare provider before you make any changes. For real, serious. Okay, so if you have innate immune system dominance, then adding molybdenum at high doses when you already are fine, you're making molybdenum cofactor, and your biggest problem is this extracellular sulfite causing all of this oxidative stress, then adding molybdenum might be fueling your neutrophils by supporting the the hydrogen sulfide producing bacteria in your gut. There is one in vitro study showing that if they give hydrogen sulfide producing bacteria that use sulfate, that's on my next slide. Or maybe it is, but if it's not, I'll talk about it again. But let's go to this person. If you, no, actually, we'll just keep going. Sorry, I'm a little stumbly. This has been a very long video. I've been taking breaks, but still, it's been long. Okay, so the reason why I get concerned about molybdenum, and I talked about in the video on molybdenum itself, but I wanted to share it in here, is that there is a new recommended reference dose for molybdenum, and it's a very small amount, works out to be about 67 micrograms for like a 70 kilogram person, which is definitely not the doses that we've been mostly using in alternative healthcare. Most of the doses are like Mozyme is 50 micrograms, but then the Mozyme Forte is 150 micrograms. And then there's molybdate supplements out there that are 400 micrograms. So we're consuming a lot more of this. And they did this study in China on the exposure to molybdenum. And they're like, look, we're seeing people have chronic kidney disease and damage to their kidneys. And there are studies about molybdenum causing apoptosis And again, it's when it's not incorporated into, and it's when it's high amounts and it's not incorporated into molybdenum cofactor. So, and we only need molybdenum cofactor for those 5 enzymes in human metabolism. So, I'm not sure quantitatively how much molybdenum that would be, but it seems like we have this reference intake, right? And an RDA. So, yeah. So my big thing is, if you're concerned, have a comprehensive metabolic panel done and calculate your estimated glomerular filtrate rate. It actually should be on there calculated. And asked to have cystatin C checked, which is an early marker of kidney dysfunction, especially if kidney disease runs in your family. Having chronic kidney disease will actually cause you to retain sulfite in your blood. And then you have this same oxidative stress problem that you're trying to solve by taking high dose molybdenum. So molybdenum isn't the only thing you need for making Moco. And that's what I'm hoping to share with you. So what about, again, those people that don't have molybdenum cofactor deficiency, but assume, because I assumed for sure, and I may have had molybdenum cofactor deficiency when I wasn't at first getting all the nutrients in to make Moco. What if I'm actually causing a worsening copper deficiency when I take high dose molybdenum? Because what can happen is you can form this thing called tetrathiomolybdate in the presence of sulfur that comes from our diet, okay, and dietary amino acids. And then that can bind to copper, and that keeps copper from being absorbed. And so, and then also you can absorb just this. This actually happens in ruminants, but in theory, this could happen in people who have hydrogen sulfide SIBO. And that would, in particular, I was telling you about the molybdate can inhibit the desulfovibrio bacteria from producing hydrogen sulfide from sulfate, but it doesn't inhibit the metabolism of methionine or cysteine into hydrogen sulfide. And the problem is, again, that was like an in vitro study, and we wouldn't be constantly inundating our intestinal tract with sodium molybdate. So I would be careful and be aware of your copper status, because you do need copper for superoxide dismutase. So one thing you could potentially do is time your molybdenum or molybdate supplements away from high sulfur foods. So you could try, if you tolerate it, you could try taking them on an empty stomach, and you could avoid copper and molybdenum foods at the same time, as well as combining these supplements. A lot of times multi-minerals will have both molybdenum and copper in them at the same time, and that is a bad idea. You need to separate them out. And you want to consider taking, okay, I already said that, molybdenum on an empty stomach. I dose my daughters in the morning with her medication while she's sleeping. She just has one medication. If you're wondering, she has non-classic congenital adrenal hyperplasia. Genes, they're my favorite. My daughter also has a massive 7.29 megabase DNA deletion on chromosome 2. And I kind of wonder if it was related to sulfite toxicity and oxidative stress. It was just a spontaneous deletion. So de novo. Okay, so here are a couple of people from our group. This is their OMX test. And this particular person had all the symptoms of sulfite toxicity and S-sulfocysteine. And the other person in the group had the same issue, same exact symptoms, okay? And a lot of the same labs, which this isn't a case study, so I'm not going to go over all of them. But they have high S-sulfocysteine levels. But then this person did not have high S-sulfocysteine levels. And you can actually see that they have low levels and they have very high cystathionine levels. And you might think, oh, well, they're just not making cysteine, but they eat dietary cysteine. And this is actually a marker for B6 deficiency. So this would go along with the lines of This person has excessive sulfite from neutrophils and excessive hydroxyl radicals, potentially from increase in iNOS. So this person definitely is struggling with oxidative stress, including sulfite, because they react to all the things that you would react to if you had sulfite oxidase deficiency, but they don't have it because the S-sulfocysteine is very normal. Whereas this person has higher levels of S-sulfocysteine, indicating that they do struggle with molybdenum cofactor or making the full sulfite oxidase enzyme. Okay, so I highly recommend doing an OMX. I've said this several times now. I didn't know this lab existed in December of this past year, but if I had known, I would have gotten it done then. I just got it done recently myself, and I do not have high S-sulfocysteine levels. So that's pretty interesting. I actually have a B6 deficiency, probably from the sulfite and neutrophils. So sulfite being produced by neutrophils. Okay. And that is the end of this insanely long presentation about a tale of two sulfites that's actually potentially three sulfites. So I hope that this helped to give you some ideas of what could be going on in your body. And love to you all. This is definitely an underwater chess game, as Bob Miller says. And I will do another video soon, I hope.